We spent yesterday talking about Euclid's algorithm and greatest common divisors, and going through some basics of number theory, understanding the idea of arithmetic modulo other numbers. And what we're going to do today is kind of build on that, go through one of the nice elementary theorems in number theory, which turns out to be, it's a very abstract theorem, it's very interesting, it's very elegant, but it turns out that nowadays it's at the heart of what makes these public key cryptography systems work. And we're going to go through this theorem, leave it on the side, make sure everybody understands what it says. We're going to prove it because it's a nice proof. And then we're going to switch gears and talk about cryptography as a topic, as a subject. And there's a lot to talk about. You can do a whole course in it. I'm just going to give you a little brief history of how people used to encode things and decode things. And then jump right into how people do it today. And basically the way people do it today is extremely secure. Is a way which is virtually unbreakable. And the reason it's unbreakable is based on the fact that nobody knows any good algorithm to factor very, very large numbers into their primes. If somebody had a good algorithm to do that, then all these cryptography methods that are popular nowadays would crumble and be easily breakable. And you'll see why you need to factor large numbers in order to break this code. And until somebody comes up with any method of factoring large numbers that works, these codes are going to be essentially completely secure. By the way, it's not known whether factoring large numbers is really a hard problem. Nobody knows whether it's NP complete, and nobody's got any good algorithms for doing it. There's a lot of research that goes into that. There are probabilistic algorithms for trying to determine whether a number is prime or not. Algorithms that don't necessarily tell you the right answer, except they got a good chance of telling you the right answer. So if you run them a lot, you get a pretty good sense of whether the number's prime, although you don't know for sure. You know for sure, within a 0.1% margin of error. That doesn't tell you how to factor the number. That just tells you whether it's prime or not. But actual factoring is a hard problem that nobody's got a good algorithm for, short of trying all the possibilities, and that's just too slow for the large numbers we're talking about. So that's where we're headed. The history of cryptography a little bit, talking about where it started, where it ends up, where we are today, why it connects to number theory, and then doing some examples. Okay, questions? Here we go. So we're going to start with a nice theorem that it's all based on, sometimes called Fermat's theorem or Fermat's little theorem. This is to distinguish it from Fermat's last theorem, which is more famous. Here's what Fermat says. He says, take a prime number p. And let A be any number not divisible by p. Here's what his theorem says. Then A to the p minus 1 is congruent to 1 mod p. That's the theorem. There it is up on the board. I'm sure it's in your book as well. It's in pretty much every number theory book. Look at it and try to figure out what it says. In the meantime, I'll do an example, and you already know what it says if you look at the example. So let's pick a prime number. Let's say, pick your favorite prime. Don't pick your, I'll pick it. Yeah, you get 5. 5 is my favorite prime. And pick any number that's not divisible by 5. Let's say 6. So this theorem says that 6, so 6 is A, 5 is P. This says that 6 to the 4th is congruent to 1 mod 5. 6 to the 4th is 1296. 1296? Ends in 6. And if you divide through by 5, you get a remainder of 1. So I want to make sure everybody knows this notation. This means congruent to 1 mod 5. That means when you divide by 5, you get a remainder of 1. That's what that notation means. Okay, that's what the theorem says. And it's true, and it always works. And the question is, why does it always work? And we're going to try to prove it and get an idea. If you understand the proof, great. If you don't understand the proof, it won't affect your understanding of anything after it. So make sure you understand the fact that the theorem's true. We'll work on the proof for about 5 minutes or so, and then we'll move on to cryptography.
Where did the 6 come from?
I just picked it out of a hat. It's any number A that's not divisible by P. Let's try another number. 11 to the 4th. Well, that also ends in 1, right? So some of these are easy to see, some are harder to see. I picked 5 because it's easy to see that it's true usually.
If it's lower, if less than P, if you have 3, 2.
Oh, that should work. As long as it's not divisible by P, anything less than P should work. Here, 4 to the 4th. What's that? 4 to the 4th is 256. Yeah. Yeah, no, it should work fine for things less than P. Other questions? All right, so why is this true? The proof is really kind of clever, and it's a good example of how you can kind of come up with very interesting theorems, and the argument as to why they're true is really, really elegant. So I'm going to do this argument in its generality. I usually do arguments with particular examples because I think they're easier to understand. But I don't think you'll miss the point if I do this in general. So here's what we're going to do, and follow me along. I'm going to convince you that in general, P is going to divide evenly into a to the P minus 1 minus 1. That if I take this 1 away from here, then P will divide evenly there. That's the same as showing that there's a remainder of 1 when I divide by P. So how am I going to do that? Here's how we're going to start. I'm going to start out considering this sequence of numbers. A, 2A, 3A, all the way up to P minus 1 times A. Just consider this sequence. In the example we just did, that would be 6, 12, 18, 24. We'd go up to 4 times 6. 6, 12, 18, 24. Maybe I should do a specific example while I do the general example. Look at these numbers with respect to 5. What are the remainders of these numbers with respect to 5? Let's write them down. 1, 2, 3, 4. They're all different. The first thing you need to notice is that is completely not coincidental. It doesn't matter whether the number was 6 and our prime was 5, so we did it 4 times. With any A and with any P, this sequence of numbers is going to give congruences mod P that are all distinct. Let's try to figure out why that's true.
But it doesn't necessarily start with 1. That's just
It doesn't necessarily start with 1, but they'll all be distinct. Now, why is that? Take any 2 of these, any 2 at all. They differ by multiples of, what's the difference between them? Multiples of A, right? 2A and 7A. They differ by a multiple of A. What I'm going to convince you is that if I take any 2 of these and I look at their difference, that difference will never be a multiple of P. If they're going to have the same congruence with respect to P, then the difference between them would have to be a multiple of P. If they're both congruent to 1, then the difference between them would be a multiple of 5. I'm going to convince you that the difference between any 2 is never a multiple of P. The difference between any 2 of these would never be a multiple of 5. Therefore, they have to be congruent to different numbers with respect to 5. How do you know that any multiple of A, 7A, 6A, up to P minus 1A, how do you know that none of them are going to get divisible by P?
P's prime. Therefore, it's not going to be, you can't use it as a factor in whatever number this is.
Well, but A could have a factor of P in it.
No, did we say A was not divisible by P?
Oh, well, that was lucky. Right. You're both right. P can never divide into A because that was our main assumption. Without that assumption, this doesn't work. So P will never divide into A. Why can't P divide into, say the difference is like 8 times A. It won't go into A, we know that, but maybe it'll go into the 8. Well, look at all these numbers that could be the differences between these guys, right? They're going to be either 1, 2, 3, all the way up to P minus 1. P can't go into something less than itself. So there's no way, if you take any pair of these and you subtract it, that their difference is going to be divisible by p. There's no way you could take any pair of these and subtract them and expect the difference to be divisible by 5. The difference between these two is 12. The difference between these two is 12. Between these two is 18. The differences are, none of them are divisible by 5. Therefore, no pair could have the same congruence with respect to 5. Yeah?
Is that because no single one of them is even divisible by 5? Is that the first thing that you showed?
I didn't show that, but it's true that no single one of them is divisible by 5.
Okay. I thought that's what you showed, how the coefficients obviously can't be divisible by 5 because they're less than it, and the a can't be divisible by...
You're 100% right. I've also showed, although I didn't mention it explicitly, that none of these could be divisible by p,
Okay.
and no difference between any two could be divisible by p. The difference between any pair is very important because that shows that the congruence with respect to p of this one and the congruence with respect to p of this one are going to be different. If they were the same, then the difference between them would be a multiple of p. And the difference between them can't be a multiple of p. That's what we've discussed.
How is it that the difference can't be?
Because the difference between any pair here has to be some multiple of a.
Oh, right.
And it's got to be some multiple of a that's less than p minus 1 multiples.
So for the same reason that an individual...
The same reason that any individual one can't be divisible by p, that's the same reason that the difference between any two can't be divisible by p. Because the difference between any two is the same as one of these individual ones. Yeah, Tony. Okay. Questions? All right, so what does this mean? It means the following. That somehow, if I figured out the congruences of all these numbers with respect to p and I wrote them down, I'd have all the numbers. How many congruences do you have with respect to p? You can have 1, you can have 2, 3, 4, all the way up to p minus 1. We're not going to get 0 here, right? It's not ever divisible by p. Now, they could be in any order we want. So we have to come up with an argument here that doesn't use any order. So here's our argument. So I didn't write this down, but you should have in your notes. Every one of these has to have a different congruence with respect to p. Okay, make that note to yourselves. And here's what we say then. So hence, I'm going to multiply all these things together. And I'm going to make a congruence equation. If this one and this one and this one and this one all together come up with all the congruences from 1 to p minus 1, I don't know what order they are. So if I multiply them all together, I know that they're going to equal to the product of all those congruences. I just don't know what order. But if I'm multiplying, I don't really care about the order. So this is going to be 1 times 2 times 3 all the way up to p minus 1 mod p. There's a's here, but there's no a's here. Right. What happened to it? Because I know that each of these individually is going to be congruent to one of these numbers, 1, 2, 3 up to p minus 1. And each of them is going to be congruent to a different one. So if I multiply these all together and I check their congruence with respect to p, it's going to be equal to the product of all the congruences together. I just don't know what order. So I might as well just write it in ascending order. Okay?
Are we positive that we're not going to skip any in there?
Yeah, because we know they all have to be different, and there's p minus 1 of them.
Okay.
So we've got to have one of each. And that's the right question to ask. That's what makes this argument so clever. We've shown that there can't be duplicates. We know we have to get p minus 1 of them, so the only choices are 1 all the way up through p minus 1. All right, so let's check to make sure this works. Okay, so what would this mean in the example that we just did? It would mean that 6 times 12 times 18 times 24 is congruent to 1 times 2 times 3 times 4 mod 5. That better be true. Well, we know that 6 is congruent to 1, and 12 is congruent to 2, and 18 is congruent to 3, and 24 is congruent to 4. So this should work, and you can multiply it out and check. When you multiply these all together, you get all terms that have multiples of 5s in them, except for the only term that doesn't necessarily have a multiple of 5 is 1 times 2 times 3 times 4. All the other terms have multiples of 5s in them. That's another way to look at it. Okay? Yeah, Teresa?
So is that what congruence is you sort of like divide out the common factor? Is that sort of, it doesn't mean anything to me. at this moment.
Congruence, these two are the same because if we don't care about multiples of 5, they're equal.
But sort of overall, what is congruence? It seems to me from what I've seen so far that it has something to do with factoring out a common factor to sort of...
Here, this is what congruence means. 7 and 2 are congruent mod 5 because they differ by a multiple of 5.
Okay.
12 and 2 are...
So to take it out.
12 and 2 are congruent mod 5.
Okay.
Okay? It's a way of saying that, it's a way of actually setting up an equivalence relation on all the numbers in the world. 2 and 7 and 12 and 17 and 22 are all in the same equivalence relation. They're all the same. Anything that differ by 5 are all the same.
Okay. That's what it's about.
Right. So what I'm saying is that none of these are the same with respect to P. They're all different. Does that make sense?
Yeah.
Okay. Joe, what's your...
No, I don't understand how those two are, how 7 and 12 are both congruent to 2 mod 5.
That's what the definition means. What this means is that you subtract 2 from 7 and you see if it's divisible by 5. Check the difference of the two and see if they're divisible by 5. Okay? Yeah, Dimitri?
And another way to think of it is they both have the same remainder when you divide by 5.
They both have the same remainder. Right, so all the numbers in the world are in 5 classes. Either they're divisible by 5, or they have a remainder of 1, or they have a remainder of 2, or they have a remainder of 3, or they have a remainder of 4. Every single number is in one of those equivalence classes. And you can prove that that relation of congruent is reflexive, symmetric, and transitive. So it partitions all the integers into one of 5 groups. You're very familiar with one thing just like this, just odd and even numbers. Right? Odd and even numbers are just numbers that are congruent mod 2. Right. Okay? So there's 2 equivalence classes there, the odd numbers and the even numbers. Yeah?
For a congruence, you can put mod on one side and it applies to the whole thing. And for an equation, you would apply mod to whichever sides you want to specify. The reason I'm asking...
Yeah?
Okay. That's a yes?
No, I was saying, yeah, the reason you're asking is?
The only reason I'm asking is for clarity. I mean, I understand what's going on here perfectly, but I just...
The only ever time you have mod p in parentheses is at the end of an equation to mean that this equality is only true modulo p, meaning it's only true if we don't care about differences that are multiples of p.
Okay.
That these two are the same if the remainder is the same when you divide by p.
And
All
you
those
never
are...
use mod p... okay.
No, I think that's the only place, that's the main place you would see it.
It's
Yeah.
the main place you would see it. You wouldn't
Yeah.
see it used in the
Well, I
other
mean,
book.
I don't know. I mean, you might see it somewhere else, but
I have like 2 equals 7 mod 5.
Yeah, but that's...
Mod 5 just refers to the...
Yeah, you'd see it like this, but that's the same as that. It's 2 equals 7 mod 5.
You ever see it as an operator, like friend 7?
Oh, in a computer program, you might see it as an operator. Right. You'd see it like this in a computer program. 7 mod 2. That has a completely different meaning.
But you would never use that.
7 mod 2 equals 1. 7 mod 5 equals 2. Right. 7 mod 2, it means what is the remainder of 7 when you divide 2 into
Use
it?
in a mathematical equation.
No, not unless it was a computer program.
You
Right.
want to use it like a multiply symbol, for example.
Well, you wouldn't use the word mod, no. In C, you'd see it like this, right? It's a percent sign, right? And in Pascal, they actually called it the word mod. But outside of the language Pascal, I don't think people generally use the word mod as an operator.
But you wouldn't use it in algebra.
Generally not, right? Well, if you did, you'd have a different symbol for it. I mean, you often talk about the remainders of things, and you'd say...
Seems like it would be useful when stating an algorithm like this to be able to specify something.
You could. You could use the word mod. You could use percent. You could use the greatest. You could use the upper ceiling. There's a lot of ways to describe mod. It's basically a division where you subtract the whole number part away. So there's lots of ways to do it.
Is that what ceiling means?
Ceiling means round up. So if you divide and then round down and then subtract, you get mod. All right. Are we back on track? Other questions? All right, so here's where we're up to. We take these numbers, we multiply them through, and presumably 24 mod 5 is going to be what? 4. So presumably if we multiply these all together, we'll get a remainder of 4, and you will. And this is true. So where do we go from here? We're actually not too far here from here. We can actually get there in a couple of steps, and then the proof's going to be done. So the main logic in this proof is going from here to here. In writing it down, I'm going to regroup here a little bit. How many a's do I have? P minus 1 a. So I got a to the p minus 1, right? Times what? Good, times p minus 1 factorial. Good. I got p minus 1 a's, and I got 1, 2, 3, 4, all the way up to p minus 1. That's this side. And I'll subtract the other side off. What do I get down the other side? P minus 1 factorial. This is the difference between the left and the right side. And if they're a congruent mod p, it means, and we write it like this, and this means that p divides this evenly. So this implies this. This means that p divides the difference between these two.
And they're different by a factor of p because they work out to the same. They're both mod 4.
Right, because they're both congruent to 4 mod 5. So when you subtract them from each other, there's going to be a multiple of 5 between them.
Okay.
So things that are congruent to 4 mod 5 would be 4, 9, 14, etc. Okay. So if you subtract any two of them, you get a multiple of 5, or in this case, a multiple of p. Joe, you had a question? You had a look on your face a second ago. Now it's gone.
I don't understand why you're doing that step, and why can't you just say that the left side is that a to the p minus 1 power times p minus 1 factorial is congruent to p minus 1 factorial. Therefore, a to p minus 1 must be congruent to 1 mod p.
I could do that, if you see that. Fine, then no reason. Then that's fine. You get it completely. I'm just trying to, I'm trying to break it up into smaller steps. This implies this, and we're trying to get to this. So we have one more step to get there. P divides p minus 1 factorial times a to the p minus 1. Did I do that right? No? Minus 1. There we go. That's what I'm looking for. I factored out a p minus 1 factorial. So if p divides this, can p divide p minus 1 factorial? All the numbers here are smaller than p. Right? There's no factor here that's as big as this prime number. So this prime number will never, ever divide anything in here. So if it divides this product, and it can't divide the first part, therefore it has to divide the second part. Okay? It's like saying a 5 divides into 4 times 3 times 2 times 1 times something else. Well, it's not going to be able to divide into any of these, so it's got to be able to divide into this one. So this implies that p divides into a to the p minus 1 minus 1. And that's exactly what this says. Okay, that p divides into the difference between a to the p minus 1 and 1. So the main step in the proof is going from here to here, and then there's just a little algebra. Let me stop. This ends this contained part of the lecture today. So we're done with this proof. If you have questions on it, I'll stop now. If you don't get the proof, it's okay. Just understand what the proof says, understand the result. And if you do get the proof, or you have some more questions, let me take them now. Yeah, Donna.
Can you maybe explain why p has to be a prime number for this to be true?
That's a good question. Whenever there's conditions, you kind of want to make sure that they're necessary, right? Why does p have to be a prime number? Where did we use it in any step?
It's like 5 steps. It doesn't divide any number smaller than that.
In this step here. Right. Baruch thinks it helps here. What do you think, Donna? What if this number wasn't 5? What if this number was 8? That's not a prime number. Then I can't say it doesn't divide here. It could divide this because 4 times 2 gives you 8. But when it's prime, I know it's not going to be able to divide any possible combinations of these because there's no way to split that number up into pieces because it's a prime number. So it's used in this step from going here to here. And Gary, maybe that's the step that you kind of internalized in your head but really needs a description. P divides the second part because P can't divide this part. And the reason it can't divide this part is because P is a prime number. Otherwise, you would get stuck here and there'd be no guarantee that P divides this part. P might divide the whole thing only because it divides this first part. Do you get it, Donna? That's a very good question, and it's a very natural question to ask. Are there other questions? You write down the alphabet A, B, C, D, E, F, G, all the way up to X, Y, Z. And now let's just shift up all the letters by some fixed amount, say by 3. So like A is going to turn into D, and B will turn into E, F, G, and Z would be C, and this would be B, A. Okay? I mean, kids do this. You get on cereal boxes, right? This kind of magic decoders, right? Magic decoder rings, right? The same idea. Now, let's say I encoded a message just like this. You had no idea how I encoded it, but this is the way I actually did it. You know, so I have a whole message encoded this way. How would you decode it? Right, there's only 26 combinations, right? There's only 26 ways I could have done it. Try all 26. 25 of them will probably be gibberish, and 1 will be a message. And you're done. You could do this by hand in a few minutes. If you had a computer, you can do it in a couple of seconds, right? It's not a hard thing to do. So even in World War II, this is obviously not good enough. Even in ancient times, this isn't good enough. You need something a little better. So here's a way to make it much more complicated, or what seems to be more complicated at first glance. A way to make it more complicated is, let's call this the D encoding, okay? Because I start with D and move away. Okay, so now let's encode this way. I have a code word called dumbbell. How do you spell dumbbell? 2 B's? Yeah. Yeah? Dumbbell. Okay. Here's the way I'm going to encode a message. Let's say I have a message, hello. Here's how I would encode it. I would take the H and encode it using the D encoding scheme. So that would turn it into a K. And then I take the E and encode it using the U encoding scheme, whatever that ends up being. And then I take the L and encode it using the M, and the other L encode it using a B, and the O using the other B. And if the message goes on and on and on, sooner or later I hit the end of my encoding word, and then I wrap around to the beginning. Everybody get the idea? This is much harder to decode. How many different possible things do you have to try, completely brute force, to decode a message that was encoded like this? If you have no idea what the code word is.
Do you know the length of the code word? You don't know anything.
If you don't know anything, you're really in trouble. So let's say you get a spy, and you figure out the length of the code word. 26, 1, 2, 3, 4, 5, 6, 7, 8, right? We can all count now. That's a lot. What if you have a code word that's 35 symbols long? It's not so practical to do this anymore. Okay, because it gets to be 26 to the 30-something. Everybody get the idea of why this is better? This really just shoots it up an exponential amount. But this is exactly the kind of encoding the Germans used, give or take. And it's exactly the kind of stuff that was routinely broken using a combination of computer help and a combination of ingenuity. So, without getting too much into the details, how would you go ahead and try to solve something like this without just brute force trying them up? Rob, you have a...
Well, you can use algorithms to look for the most common letters, patterns of commonality, even through a pattern like that. Not that I know the algorithm.
Okay, that is actually one of the main ways they do it. Maybe I should follow up a little bit and be specific about Rob's suggestion. Here's one method. Every language seems to have some frequency of how often the letters show up in typical messages. Everybody knows this if you watch Wheel of Fortune.
RSTLN.
right? And it's you know this because in Wheel of Fortune, when somebody gets up there, you know, and I don't know, what do you have to spend some money to buy to get a letter or something? So you get a letter and you guess Z. Is there a Z? And it's just like the crowd groans. Get a clue, right? Z. No, I mean X. I mean Q, right? So everybody knows that some letters come in more frequently. And you can do this very scientifically. You can say in theater productions, the letters group in this way. In letters, one to another, the letters group this way. The percentages might be a little off. In certain types of ways of expressing yourself in a particular language, you get this many percentage of E's, this many percentages of F's, this many percentages of D's. You can do this, and you can get people to calculate it for you. So how does that help? Here's how it helps. Let's go here to the H. The H was encoded using D, right? Now let's move on. 1, 2, 3, 4, 5, 6, 7, 8. The 8th letter is also going to be encoded using D. So you take the message that you intercepted, you take the 1st, the 8th, the 9th, 1, 2, 3, 4, 5, 6, 7, 8, right. The 1st, the 9th, the 17th. You take a whole equivalence class of letters. 1st, 9, 17, 26, 35. You take all those letters, you put them in a big group, and you look to see what happens when you encode them on each of the 26 possible, decode them in each of the 26 possible ways. Which one gives you a collection of letters most like the ones you expect to have in the language that you're decoding? Which one looks most like German? Now when you do this, you get a lot that might look like German. Maybe 3 or 4 of them look like German instead of all 26. So now instead of 26 chances here, we got it narrowed down to just 3. And maybe here it turns out that 1 is really strikingly like German, the rest are not. So this goes down to 1. Suddenly the 26 to the 8th goes way down to something that you could actually do with a machine or by hand. And that's more or less how they went ahead trying to break the codes in a hit or miss kind of fashion, ad hoc, hoping that by these percentage tricks they could get it down to a reasonable amount they could actually look at. Yeah, Baruch. Yeah.
I think they were supposed to switch the key very frequently.
Right.
I think what helped them at some point that they either because of sloppiness or whatever
Started using the same one?
they used the same key for extended period, which gave them enough time to
Right. If you switch this key, right, you need a lot of data to get good information. So if you keep the key for a long time, you're going to be dead because the people will get enough data and be able to decode it. At the same time, the other thing you want to switch is the length. If we don't know the length of this keyword, we can't do this at all. We don't know what the equivalence classes are. We don't know that it's the 1st and the 9th and the 18th and the 2nd and the 10th and the 19th. We don't know what to do. So getting the length is very important. Predicting the length of the next keyword is important. And that was done with a combination of espionage and all sorts of other tricks, guessing the method they used to pick the length of the next keyword.
The length, I don't think the length of the keyword is that hard, because I think what you do this is from the code book, which I have Michael's copy that's not sitting on my
Yeah.
desk, but it goes through the whole history and how they broke it.
Uh-huh.
But I think what they did to figure out the length is you look for repeated combinations of letters. Because there's a good chance the is going to be encoded a lot. So maybe you'll get 3 or
That's
4
true. So good. So you can make backward inferences as to what the length of the keyword is based on repeated letters. That's true. Next stage. All of these encryption methods, at least theoretically, with enough computing power, can be decoded if you guess well enough and you have some help. Certainly, if you have a good spy, you're completely dead. If you steal the code word, then decoding it is trivial. Right? You just go backwards. So the goal is to get an encoding scheme where you can publish the encoding scheme in the newspaper so everyone knows how to encode the message. But even though you've published the encoding scheme in the newspaper, nobody can easily use that to go backwards. Now it seems like that's impossible at first glance, because if I publish the code word, everybody can go backwards. Okay, adding numbers modulo 26, which is what we're doing with this alphabet code, is the same as subtracting numbers modulo 6. There's no difference. It's the same arithmetic. It's just as easy. So we need to come up with a function that's different than adding numbers modulo another number, because the inverse of that, subtracting numbers modulo another number, is too easy. We need to come up with a function whose inverse is hard. Okay? So squaring numbers, the inverse is square rooting numbers. Whatever you can do forward, it seems you can do backwards. So we need to come up with an example that you can't do easily backwards. All right, and that's what is done today. You publish the public way of encoding. Anybody can encode it, but just because that's published doesn't mean anybody can decode it. Everybody is stuck for decoding it. So everybody can encode something, hand it to the person next to them, and ask them what was this when it started, and none of the people would know, even though they had just encoded something themselves. All right, that's the idea. We're going to show how this works. All the details. I mean, nothing will be left out. All right, questions about this? All right, so how do you use something like this? If you have something like this, then you can buy stuff on the internet, even if you're a paranoid lunatic, right? It doesn't matter. You can think that the whole world is wanting to steal your credit card, and you would never, ever, like, leave a carbon in the old days, like in a garbage can. You'd rip it into shreds. If you're a person like that, you are completely safe, because you encode your credit card with a publicly, printed algorithm, and you send it over the internet, and nobody can decode it. Well, somebody's got to decode it, right? So there is a way to decode it, but you need special information. That information is secret. That information is in the hands of one particular person. So say you have a company and they want to take orders by credit card. They hold the secret piece of information that helps them do the inverse, the decoding, in a vault. They use that to decode, and they publish in the newspaper the way you encode it. So everybody can send them their credit cards, and only they can figure out what the credit card numbers really are. So suddenly you can buy securely. All right. Another way that this is used is a way that doesn't seem obvious at first. I'm not going to show you how to do it yet, but I'll show you another way to use it. What if I don't want to just send secure information? What if I want to send something to Chris, and it's not particularly secure? I don't really care if anybody sees it, but I want him to know that it's from me. Okay? He sent, say he went on vacation and he sent in a problem set, and he wants to know whether I got it. So I want to send a message that says, yes, I got your problem set. I don't give a hoot if anybody sees that message, but I want him to know that that message came from me and that nobody just forged it and wants him to think that his problem set got there. You can imagine this is very important, right? I mean, this is for signatures. I want to close a real estate deal, right? And nobody really cares about the details of the deal, but you want to know that I signed it, that I saw this deal and I said, okay. You're on the other end. You want to verify that it came from me. So how do you do that? You can do that with the same scheme, even though it doesn't seem like you can. So here's the trick. We have this public encoding that anybody can do, and we have this private decoding. So here's how I can send a message to Chris and make sure that it works. I publish a public encoding out on the world. Anybody can see it. It's on a web page somewhere. And I keep the private thing for me. And I take my name, Shai Simonson, and I decode my name with my private code. I turn it into something else, some encrypted ugly thing that it came from. And then I send that privately decoded name over the internet at the end of my message. And Chris sees it, and it looks like gibberish. And he runs the public encoding program to encode it, to see what it turns out to be. And if it turns out to be Shai Simonson, then he knows it's from me. How come? Because nobody could conceivably come up with the decoded version of my name because they don't have the private information. Nobody could figure out what Shai Simonson would look like if it got backward decoded. So I can guarantee that it was me. Now the thing is, if I routinely do this and I just use my name, it gives people an infinite amount of time to sooner or later figure out what this is, and maybe they could figure out my private information or steal it somehow, and then they'll know that my name decodes back to this particular XYZQ, and they'll send XYZQ to anybody and they'll forge my name. So the way this is actually done in practice is instead of using your name to decode, you send a message, some arbitrary message, and you make up some public function about that message, like count the number of E's in this message. And you turn that into a number. And then you decode that number and send it to Chris. Chris can count the number of E's in the message. He knows how many there should be. He encodes that number I sent him, and if the encoding matches the actual number of E's in the message, then he knows that it came from me. Because I'm the only one who would know how to take that number of E's and send it back to the originally encoded message. Yeah, Baruch? Yeah.
If somebody intercept your message, I guess it could actually pretend it's you, right? I mean, this is.
Well, but if he could intercept the message.
Intercept the message.
And steal the.
Right. Just send it.
But that's true. But if I did it this last way I just described, he could only intercept my message and impersonate me for this particular message. He could send any message with that number of E's in it if he knew that.
He knew that it was specifically the number of E's.
Right, but that's public. That information's public so that Chris can use it. And right, he could send any message with that particular number of E's in it. Right. But the idea is that particular function I talked about, the number of E's, it's typically some hash function that means it takes this big message and turns it into some number. And say we change it every week.
I mean, hash functions normally go to 128-bit numbers, so there's a number for every atom in the universe kind of thing.
Right. It could go to a lot of different possibilities. His computer calculates which possibility it ended up being. I do it too, but I decode it. And he's the only one who can check that it came from me. Well, anybody can check that it came from me, but I'm the only one who could have decoded it to begin with. So everybody get this idea? This idea is a little tricky. You can do both these ideas. If I have my own public-private scheme and somebody else has their public-private scheme, I can use their scheme to encode a message. I can use Chris's scheme to encode a message publicly and send it to him. He's the only one who'll be able to decode it. I use my private scheme to decode my signature or a hash function on the message. When he gets it, he uses my public encoding to encode my name to see if it's the same as a hash function. And he uses his private decoding to decode the message that I encrypted. So you can send messages securely and you can have the name or signature be completely verifiable. This version is going to be possible if you have the public information to figure out the private information. Then I'm just going to turn the dial up a little bit, and that version is not going to be easy to get the private information. So I'm going to get you started on an easier example where you could figure out the private information if you had the public information, where you could decode if you knew how to encode. And then I'm going to show you how to just turn it up a little bit, and the decoding stuff gets too hard. It requires factoring really big numbers. Okay, questions so far? All right, so here's how we're going to do it. In these examples, we're imagining that our messages are all converted into numbers. And the numbers are then converted into other numbers. So we send everything as numbers. It just makes it easier to present the whole idea. So if you have a message of characters, convert all those characters to numbers in some particular way, run it through your encoding scheme, send the new numbers to somebody else, they convert them back to the numbers you sent, and then convert them into letters. All right? So here's how it's done. You start by picking a prime number, any number at all. Let's say 17. And then you pick another number. Choose, let's call it E, such that the greatest common divisor of E and 16 is 1.
By E, you just mean any variable.
Right, I don't mean 2.71828. Right. E for encoding. Choose an E such that the greatest common divisor of E and 1 less than this number, the 16 is P minus 1. I'm doing a specific example, but you could do it in general with any prime number. Choose a number E such that the greatest common divisor of E and 16 is 1. So I'm going to pick E equals 5. E.g., for example, E equals 5. This isn't too involved, so don't expect too much more. It's actually almost here. This information, the 5 and the 17, this is the public information. This gets published in the newspaper or on the web, someplace where anybody can get to it. That's the information we need to do encoding. And I'm going to show you how you do encoding now. So let's say I want to encode some number. Let's say 6. You take 6, you raise it to the 5th power, to the eth power. Oh, this is what Tony's asking before. The answer is yes to your question. Do you ever use mod as an operator? You do. 6 to the 5th mod 17 means what's the remainder of 6 to the 5th with respect to 17? Yeah. Well, here's a straightforward answer. Finally, I understand what you're asking. 6 to the 5th mod 17. That means take 6 to the 5th, divide it by 17, and tell me what the remainder is. Okay? Anybody know what that is? I know what it is. What is it? Yeah, that's between 0 and 16. So what is it? It's 7. Get a computer to do it for you. All right, questions so far? Well, that's it. Now you know how to encode numbers. Somebody publishes this information. You take the thing you want to encode, you raise it to this power, you mod by the 17. The 17 is the prime, this power is the e. You have to know which number is which. You don't want to do 6 to the 17 mod 5. You have to know that this is e and this is the prime. So it's given to you in order. Right? You're told that this is the exponent, this is the prime. That's how you do encoding. All right. Questions so far? The question is, how do you decode? And with this, we're going to come up with a whole issue of how to make sure the decoding is hard. Encoding is easy if you have this information. How do you decode? You get 7. You're wondering, what message was sent? 7. I wonder what this person really meant. They really meant 6. But how do you figure out that they meant 6? The reverse function is very similar to this function. It's going to be 7 to the something mod 17. And in particular, the number here is going to be 13. That's the secret code. I'll call this private information. Private info is 13. 17. 17 is really public, so I'm going to circle the 13. The public needs one number and the prime number. The private person who's decoding needs the public prime and another special number. If you do 7 to the 13 mod 17, you get back to what you started with. Now I'm going to tell you where that 13 comes from, and I'm going to tell you why this works. And then we're going to figure out how hard it would be to figure out 13 given just 5 and 17. Okay, so far, right now, this is just magic. You can check this and see that it works, but it does. All right, so. Questions so far? Okay. Let me show you where the 13 comes from. Then I'll show you why this works. Let's call that 13 D. Here's the 13. You want to pick a D, a private piece, such that when you multiply D and E, you get something congruent to 1 mod 16. If you're wondering why the hell would you want that, it's very important. This condition is what makes this thing work. And you'll see why in a second. But for now, let's just understand what it's saying. In our particular example, E is 5. So we want a number such that 5 times that number is congruent to 1 mod 16. This 16 is 1 less than the prime we started. Okay, so if it was a general prime, it'd be p minus 1 there. Well, let's do this in our heads. What number times 5 is congruent to 1 mod 16? Well, the answer is 13. 5 times 13 is 65. If you divide 65 by 16, it goes in 4 times with a remainder of 1. That's how you get D. Does that seem like it's hard? Does it seem like it's easy? We'll get back to that in a little while. Okay, but that's how you would compute D.
And is the 5 from your public?
The 5 is the public information, right. We'll get back later and figure out how to compute D in just 5 minutes. But let's go back here and see why this works. Are there questions so far?
Is that the unique number?
It's unique with respect to 16. You could add multiples of...
You pick the smallest
you,
one.
Right. You pick the one between 0 and 15. It's unique with mod 16. Yeah. It's unique. Okay. By the way, there doesn't even have to be a D if 5 and 16 are not greatest common divisor 1. Remember I said 5 and 16 have to be greatest common divisor 1? The reason for that is that there's a solution to this equation. If 5 and 16 are not greatest common divisor 1, if it's like 5 and 25 or something, then there might not even be a solution to this. So it's important that that condition is true at the beginning so that we get a solution to this. And we'll talk about this solution, how we do it, in a couple minutes. But first let's go back here and convince ourselves that this works. The reasoning that this works is the way that the real one is going to work. So concentrating on this next idea is going to help you just zoom through the actual idea in a couple of minutes. Why does this stuff work? Here's what we have to show. We have to show that if you take your hidden value, let's call it m, and you raise it to the 5th, 6 to the 5th, and then you take that, you get a 7, and then you take that 7 and you raise it to the 13th, that you get back to what you started with. So we want to show that if I take m to the 5th and then I raise it to the 13th, so m to the 5th to the 13th, that's m to the 5 times 13, that's going to be congruent to first to the 5th, then to the 13th, gets you back to m, gets you back to what you started with. Mod 16. Mod 17, sorry. If I can prove that to you, then I know encoding followed by a decoding is going to get you back to what you started. That this is going to be the encoding and that's going to be the decoding. That they're inverse functions of each other. First due to the 5th, then due to the 13th. You start with 6, you end up with 6. Why is that true? I'm going to convince you this is true, and it's based on Fermat's little theorem. Questions so far? This 5 times 13, what do you know about it? What do you know about that 65? (16 times 4 plus 1). How do I know that there's going to be a remainder of 1 here? Right? I constructed these two numbers, 5 and 13, specifically so that they would be a total of 1 more than 16, that they would have a remainder of 1 with respect to 16. So when I multiply them together, I can write them as 4 times 16 plus 1. Right? That comes from this computation. So now I have that m to the 5 times 13 is m to the sum multiple of 16 plus 1. Well, where do I go from there? I've used my one main assumption. I'm out of assumptions. All I got left is Fermat's little theorem here. I better be close to done. M to the 16 times 4 plus 1 is m to the 16 times 4 times m. What do you know about this? If this turns into 1, congruent to mod 17, then we get m as our final answer. How do you know that this is going to be 1 mod 17? How do we know that m to the 16 times 4 is congruent to 1 mod 17? Fermat's theorem says, give me any number that's not divisible by 17, then m to the 16th is congruent to 1. Right? That's what Fermat's last theorem would say, that m to the 16th is congruent to 1. But if m to the 16th is congruent to 1, then if I multiply it by itself 4 more times, it's just going to be 1 times 1 times 1 times 1. It's still going to be congruent to 1. So this part is 1. This part is congruent to 1 by Fermat's last theorem. So the whole thing, m to the 65, is congruent to m. The whole thing works because this piece here ends up being 1 because of Fermat's last theorem. Questions about this?
And m is small enough.
M is not divisible by 17. We pick a number so large that our m's are always smaller. Yes. Right. If m was divisible by 17, this wouldn't necessarily work. So we make sure that m is smaller than 17, and we're safe. Yeah, Brian?
I'm just having a hard time remembering exactly what congruence of 1 means. It seems like a silly problem, but does that mean that there's going to be some multiple of 1 in the remainder?
It means that the remainder, when you divide through by 17, is 1.
Is exactly.
Right. If I take this, say, 6 to the 64th, and I subtract 1, and I divide it by 17, I get an even value. Clear? Makes sense? Okay. Other questions about this? Okay, so let's review. The public information is 5 and 17. The private information is 13 and 17. The 13 is the number that satisfies this equation. And I convinced you if I first go through and take my message and raise it to the 5th, to that E, and I do a congruence mod 17, and then I raise it to the D, I get back to what I started with, because the multiples of 16 here end up being congruent to 1 mod 17. So the only thing that's left over is an m, which is what I started with here. So the whole thing works. These two are inverses of each other. It's a really cool thing. But the question is, how hard is it to figure out D once somebody's published 5 and 17? How hard is it to figure out 6 if somebody tells you 5 and 17? How hard is it to solve this equation? How hard is it to figure out 13? Right. Well, let's see. Let's pretend I didn't tell you the answer was 13, and we try to solve this equation. What does this equation say? It says, find me D such that 5D minus 1 is divisible by 16. Right? Equals 16 times, pick a letter, P. Some multiple of 16. Or find me D and P such that 5D minus 16P equals 1. Have you ever done anything like this before? Yes, right? That's what we spent the whole day yesterday doing. You know that 5 and 16 have a greatest common divisor of 1. That was a big assumption we made. If it has a greatest common divisor of 1, you can find a D and a P to make this equation equal 1. So finding D, given E, is as straightforward as using Euclid's algorithm and doing a backward substitution. In fact, it's easy. It's not hard to get the inverse. If I publish 5 and 17, then anybody with a computer in about 3 seconds can say, hey, the private one is 13 and 17. So this is at the point where we need to just turn up the volume a little notch. The same exact idea can be milked one step further, where the computation of the 13 becomes very hard instead of very easy. Okay? So here's the main idea. So stick with me. Don't get tired right now. This is the most important part. The next step does this. It publishes, instead of publishing 5 and 17, it's going to publish 5 and some big, big, big number which is not prime. I'm not going to use a big number because it's going to be impossible to show you the example. I'm going to use a small number, but you can imagine that the number is very big. I'm going to publish the number 34. Normally, you would publish a number which is a product of two 128-bit prime numbers. Okay, a huge number which has huge factors, hard to factor. I'm publishing 34. You could all factor it to 2 and 17. I'm going to convince you we're going to do the same similar trick. But when this number is published, we can't do anything until this number gets factored. Since we can factor this number, we'll be able to go through the whole thing and recompute the private key. But if you couldn't factor this number, you'd be stuck. And I'm going to show you why and what point this all happens in just a second. So that's where we're headed. Questions about this? All right, so the private key is no longer known. It's a mystery. And now we've published 5 and 34. Just as before, if you want to encode 6, it's 6 to the 5th, but this time it's mod 34. Instead of mod a prime number, now it's mod some other big number, which is a product of two primes. I'm going to write here a product of two large prime numbers. This is not a great example of that. 2 and 17 are not large. 2 is about the smallest prime number you can get. But normally these are two really big prime numbers. You multiply them together. So there's only two factors in this huge number. Okay? Finding them would be hard. And you encode the same way. And you're going to decode in a similar way. 6 to something mod 34. And I'll tell you the secret. The secret is that the private code here is also 13. So you would decode this way. Actually, this ends up equaling did I do this one? Hold on. I'm looking at my notes. I don't remember, but I'll just write it this way. I'll call this x. I'll call this x. To encode, you're raised to the 5th power. To decode, you're raised to the 13th power. The question is, how do you find out this 13? The computation of the 13 in this situation is going to be harder. It's going to have us required to be able to factor these numbers. Yeah, EJ.
You don't use x when you're decoding.
No, I'm just saying, you take whatever you want and you decode it this way.
It's not the same.
I'll call it y, yeah. Yeah. Yeah, this would be m and this would be m inverse. Yeah, yeah. I should use a different letter. Okay. Set? All right.
24, if you care.
What's 24? Oh, this?
You don't want to use.
Oh, okay. So
60 codes to 20.
60 goes to 24, and this one codes back to 6. Okay. I don't think we need it, but we can go on. Okay. Where does this 34 come from? I said it comes from two primes. In this case, you know the primes are, we'll call them P and Q. 2 and 17. Before, we subtracted 1 from our single prime. In the 2 prime situation, we're going to subtract 1 from each of these. So we get P minus 1 times Q minus 1. And that's 1 times 16, and that equals 16. I set this up so we get the same 16 that we got before, so we don't have to do a lot more calculations, that we get the same 13. But normally, you would find the 2 primes, you'd subtract 1 from each, you would get 16. And now you would solve the following problem. 5 times D is congruent to 1 mod 16. Same thing we did before. And D is therefore 13 by using the same methods we did before. The difference here is that we didn't get to this equation until we did this step over here. We didn't know this number 16 until we first did what? Until we first took 34, factored it out, subtracted 1 from each, and multiplied them together. You can't get to this point until you factor a very big number. This step here is the slow step. We can't figure out D until we do this factoring of 34. Factoring is a very hard thing to do. You take 2 huge numbers, multiply them together, get something here, and then give it to somebody and say, what 2 numbers did I start with? And they can sit for 3 weeks, and they won't be able to do it. So multiplying 2 prime numbers is easy. Extracting them once they're multiplied together is very hard. So I need to still convince you that this does the inverse of this. That if you do x to the 5th and then you do x to the 13th, that you still get back to x, even if you do it in this peculiar way, where the D is computed via the 16, which came from a P minus 1, Q minus 1, instead of just the original single prime. Why does the whole thing still work? And that's going to wrap the whole thing up. So before I do that, let me stop for final questions. Then I'll do that. It'll take 5 or 10 minutes, and we'll be done. Are there any questions so far? We set it up the first way, just relative to a single prime, and it turned out that it ended up with this equation, which we could calculate the private value for.
How do we calculate D there?
The same way we did before. You calculate 5D minus 16P equals 1. You calculate 2 values to make this true. And that's what we did yesterday with Euclid's algorithm. The same exact way we did it before. The question is, how did we know it should be 16? And that takes a lot of work because we have to factor to find that 16.
So if you have a list
Sham, yeah.
of all the known prime numbers sitting somewhere, you could just start multiplying to find out what factors.
Yeah, there's a lot of prime numbers.
You should be able to.
You mean your idea of factoring to a large number is to try every pair of primes and see if they work?
I mean, look at the number of digits and roughly.
That's an algorithm, and it would take a long time. Yeah. Let's check this and see that it works, and then I'll stop for final questions and we'll wrap up.
The 34 you have here is the 16 here?
The 34 is what's published now.
Right.
And the 16 is calculated from a factoring that lets me calculate the private code. The private code comes from this equation with respect to 16. The 16 was calculated by factoring the numbers and subtracting 1 from each and multiplying them together.
Oh, and the 2 times 17 is 34. Okay.
Right. The 2 times 17 is a 34. The 2 times 17 came from factoring the 34. So the only thing left to show is that this whole thing still works. That the x to the that the y to the 13th is really the inverse of the x to the 5. That they really are backwards. That they do the opposites of each other. So let's go through the argument again, because it's the same argument as before with one little twist. 5d is congruent to 1 mod 16. 5 times 13, 65 is congruent to 1, is remainder of 1 with respect to 16. The same reason as before, because of this equation. So up till here, it's the same argument as before. And we want to show now that this whole thing is 1, but this time we want to show that it's 1 not congruent to 17, which is immediately from Fermat's little theorem. We want to show that this is congruent to 1 mod 34. Everybody see the difference? That's the only place where we have to make a different argument. So I'm going to write this down over here, get a little bit of room, and analyze it, because it's not too tough. We're hoping that x to the 4 times 16 is congruent to 1 mod 34. If that's true, we're all set. Now we know it's congruent to 1 mod 17, because Fermat's last theorem says you put a 17 there, and x to the 16th is going to be 1. Multiples of it are also going to be 1. So now what happens with a 34 there? Are we just dead? I mean, it still works out. So how can we prove that it works out? Well, let me write down what we do know. We know this is true, right? That's from before. What about this? Is that true? If it is, why? And if it's not, why not? Is that going to be true, that the other prime number?
No. It's got to be an even number.
Because x to the 16.
You could rewrite 16 as 2 minus 1 times 17 minus 1.
Now let's look at EJ's idea. You want to write 16 as
2 minus 1 times 17 minus 1. That's where we got the 16 from.
In other words, it's the same as 1 times 16. What EJ's pointing out, where did we get the 16 from? It was p minus 1 times q minus 1. Right? So it's 4 times 16. Maybe it's hard to see it with the 2. What if it was, let me stick with the 2. That's 16 times 1. So let's try to use Fermat's little theorem again. If there's a 2 here, what number can you put here? What exponent can you use? 1 less than it. Right? So there is a 1 explicitly there. We don't write it in. 16 times 1 is 6p minus 1 times q minus 1. So Fermat's last theorem, little theorem, says that x to the 1 is congruent to 1 mod 2. So multiples of that are also going to be congruent to 1 mod 2. This is completely symmetric. P minus 1 and Q minus 1 are together making up 16. So they both appear here times 4. This one's going to be congruent to 1 mod 17 because 16 is 1 less. And this is going to be congruent to 1 mod 2 because 1 is 1 less. I want to show that x to the 64th is congruent to 1 mod 34. And all I've shown now is that it's congruent to 1 mod 17 and congruent to 1 mod 2. Let's remind ourselves what this means. It means I've got some big ugly number here. I don't care what it is. Call it whatever you want. X to the 64th. Let's give it a name. Let's call it B for big and ugly. I know that B minus 1 is divisible by 17, and B minus 1 is divisible by 2. Okay, the B is x to the 64th. You got some big number. It's divisible by 17. That's a prime. It's divisible by 2. That's another prime. Therefore,
what's your B? Is your B
the B is x to the 64th. That's the B. If you ever have two prime numbers, and they each divide into some other number, then their product also has to divide into that number. You can prove that if you want to, but it's kind of logical. When is this not true? What if they're not prime? Can you give an example where it doesn't work? What if 4 divides into a number and 6 divides into a number? Does 24 divide into the number? 4 divides into 12, 6 divides into 12. 24 doesn't divide into 12 because they're composites. So little pieces of this can combine together in a way that you wouldn't necessarily expect. There's overlap in the factors. But if these two are prime and they each divide into here, that means that prime factor has to be a part of this, and this prime factor has to be a part of this. So their product must also divide into it. Therefore, 34 also divides into x to the 64th minus 1. 34 also divides into b minus 1. Therefore, this is true. Because these two numbers, 17 and 2, are prime. Yeah?
I'm still not clear how we proved that that x to the 64 is equivalent 1 mod 2.
It's also by Fermat's little theorem. By Fermat's little theorem, if there's a 2 here, then anything to the 1 is going to be congruent to 1.
Okay.
So x to the anything is congruent to 1. X to the 1 is congruent to 1. Multiples of that will also be congruent to 1. It's maybe not the best example to see it with a 2, but pretend this was a 15 instead of a 2. Then the numbers here would be 4 times 16 times 14. And then there'd be a 14 here and a 15 here. And then it would work the same way. The trick here, it's really kind of, I showed you the first case because the first case was around before the second case was. And the real breakthrough was really a simple idea. It was just taking the first case, adding an extra prime minus 1. Instead of p minus 1, throw in a factor of q minus 1. And everything works exactly the same as it did before, except now, before you can solve for that d, you need to factor these numbers to get your p minus 1 times q minus 1. And it's that factoring step that makes the whole thing hard. So it was a clever way of taking something that worked before that had an easy inverse, doing a teeny twist on it, and making it have a really hard inverse. And this is exactly what's used today. The numbers they choose are typically, this is what you go by in your new browsers, 128-bit encryption. Which means that after you multiply these two numbers together, the two large primes, you get a number that's 128 bits long. So that's, how many base 10 digits is that? Base 2, it's 128 bits, so it's about 3 point something, 3 point something digits for 10, so 40 or so? Something like that. 40 some odd base 10 digits. So it's a very big number. And you have to be able to factor that. And I think that's on the order of 50 years to factor a 128-bit.
That's just a small one. You can get 4096 on big systems.
Uh-huh. So that's like centuries. Right, that's centuries. As far as anybody knows, maybe there's a good way to factor numbers. If you come up with an algorithm that's polynomial for factoring numbers, that'd be really interesting. And I got to tell you, for those people who sit around and try to solve NP-complete problems, you're a lot more likely to find a polynomial algorithm for prime numbers, in some sense, than you are to find a polynomial algorithm for an NP-complete problem. Because prime numbers aren't NP-complete. So maybe there's a chance. I should say there's another reason why you wouldn't expect a polynomial number for prime numbers, but it's a little complicated. The complement of the problem is, forget it. We'll do it in theory of computation. Yeah?
Do people change encryption keys to be on the paranoid side?
I don't know. I don't know what's really done. I don't know what companies really do.
It flips with every request. That's how secure, like HTTPS works.
Mm-hmm.
The key changes at every request.
So anytime you send your credit card number, it's using a different key to encode it.
And actually, there's a transaction sequence where light encryption is used on a pre-key that builds up a heavier encryption with another key that builds up the transaction encryption scheme, the full key.
Oh, that's interesting. Oh, yeah, I should.
I mean,
actually, when you
that's what I read is done.
when you encrypt anything, I mean, we did these examples with just a single number being converted to another number. But what typically happens is you get these kind of partial sums in a message. Your message is a collection of these numbers. So you encrypt the first one, and then you connect that with the next one to give you a larger number. Then you encrypt that, and you connect that encrypted one with the next one to give you a larger one. So you embed the encryptions one in another, rather than just encrypting them, I think, one at a time. So if you have like a sequence of 100 numbers, you just don't encrypt each number one at a time and send them. You encrypt one, concatenate it with the next one, encrypt that, etc., and just embed it. I think that's how it's actually done. But I'm not sure. Questions?